We are continuing with exercise 3. We started out with the polynomial you see here, the fourth degree polynomial, and we found 1 0 and 1 factor, and so we were able to break this down a little bit. Now to continue, we're not going to work with the original polynomial, but do you see that at this stage now we can work with just what that quotient was, x cubed minus 2x squared minus 2x plus 4. It's like its own little problem or subproblem, you might say, of this larger exercise. And it's got its own list of possible rational zeros, which will be a little bit less complicated than the original polynomial, right? Because our p over q for this polynomial would be just factors of 4, plus or minus 1, plus or minus 2, plus or minus 4, over factors of 1. And so the list is a little bit shorter than it was for our original polynomial, right? Plus or minus 1, sorry about that. And so we're kind of, in a sense, back to synthetic division, but we're going to work with x cubed minus 2x squared minus 2x plus 4, and we're going to look for zeros of that polynomial. Now, can you see that there's no need to check 1 or negative 1 again? Because if they didn't work out as zeros of the original polynomial, there's no way they could turn out to be zeros of the third degree polynomial factor we're working with now. If they were a zero of this, they would have been zero of the original. So any number that didn't work, you do not need to try again. But we do need to check 2 again. And you say, but 2 worked. We already found the factor of 2. Well, there could be another factor of 2. So when a number works, you really got to try it again. You can't just give up on it, because you could have many factors of 2, actually. So we are going to try 2. And so we're going to set up our synthetic division box. Now with the coefficients of this polynomial, this third degree polynomial, 1, negative 2, negative 2, 4. And the nice thing is you work through these steps, it gets less and less complicated, right? Because you get smaller and smaller polynomials to work with. 2 times 1 is 2. Add these together, we get 0. 0 times 2 is 0. Add these together, we get negative 2. Negative 2 times 2 is negative 4. Add these together, we get 0. Up. So we have another factor of x minus 2, right? So, because if we plug in x minus 2, it has to be a factor of this cubic, and because of the 0 we got there. We didn't give that polynomial a name, but we're saying if we plug 2 into this polynomial, we'll get 0. So 2 is a 0 of this cubic. And the quotient here is x squared plus 0x minus 2, which we're just going to write as x squared minus 2. All right, so let's sum up what we got. I'm going to go back to the original just so we don't lose sight of it. We broke that down into x minus 2 times x cubed minus 2x squared minus 2x plus 4. And now what we're saying is we had that original factor of x minus 2. Now we have another factor of x minus 2. And this a third degree polynomial will factor into x minus 2 times x squared minus 2. Okay. So now what we see is we got two factors, each of x minus 2, and we got to finish up with this quadratic. X squared minus 2 is not a difference of squares. That cannot be factored, but to find any remaining zeros, now just because it can't be factored doesn't mean there are no zeros. To find any remaining zeros, set x squared minus 2 equal to 0 and solve. So if we set x squared minus 2 equal to 0, x squared is equal to 2, x is equal to, there are two square roots, plus or minus the square root of 2. There are two more zeros, square root of 2 and negative square root of 2. These are real zeros that are not rational zeros. Rational numbers are integers or fractions of integers. So that rational zero theorem, this thing is limited in its use because it's only going to tell us about zeros that are either integers or fractions of integers. The rational zeros theorem is never going to tell us about these square root zeros. And so that's unfortunate, but that's just the way it is. Now, so what did we find out here? We wanted to find all the real zeros, so let's write an answer to this problem. The real zeros of f of x, our original function, are, well, we found 2, and in parentheses I'm going to say with multiplicity 2. And the multiplicity just means with multiplicity 2. I'm trying to get a 2 in there. Because the multiplicity tells us that there were two factors of x minus 2. And then we got square root of 2. And then we also got minus square root of 2. Those both had multiplicity 1. And the reason we want to mention the multiplicity here is our original polynomial f of x was a fourth degree polynomial. We kind of expect 4 factors or 4 zeros, and we only get 3 numbers here because it's kind of like 2, the 2 is repeated twice, right, because of those 2 factors of x minus 2. Now we're done with the problem, but I still want to say a little bit more extra. And there are two comments I want to make. So we're just going to call this extra comments. So we had our function f of x equals x minus 2 times x squared minus 2. And we said the zeros were 2, square root of 2, minus square root of 2, that 2 had multiplicity 2. And now what about the factor theorem? The factor theorem that we had along the way said x minus k is a factor if and only if k is a 0 of p of x. So we're saying these square roots are zeros of the polynomial, but where are their factors? The factors we see here are factors with integers. if we allow square roots, we actually can factor f of x further. So I have x minus 2 times x minus 2. Because these are zeros, x minus square root of 2, and now x minus a negative square root of 2, which will be x plus square root of 2. Here is a fully factored form of our original fourth degree polynomial. If you don't believe me, just imagine what would happen if you multiplied this out. You get x squared plus square root of 2x minus square root of 2x minus square root of 4, square root of 2 times square root of 2. These cancel out, and we're left with just x squared minus square root of 4, which is x squared minus 2. So sure enough, those two factors multiply out to be this x squared minus 2 up above. So I just want to make one comment about how that's the fully factored form, where you see the relationship between the real zeros and the factors that correspond to them. And just before we finish, what would the graph of f look like? We know we have x-intercepts at x equals 2 square root of 2 minus square root of 2, and square root of 2 is about 1.4. So I'm just going to draw a rough sketch, very rough sketch by hand. 1, 2, -1, -2. So we have a 0 at 2. Square root of 2 is about 1.4. So between 1 and 2. And negative square root of 2 is between negative 1 and negative 2. The end behavior, because this is a fourth degree polynomial function, is going to be like y equals x to the fourth, because our lead coefficient is positive. So from this 0 on the right, the graph has to rise up. From this 0 on the left, the graph also has to rise up. The x-intercept at x equals 2 has multiplicity 2. So we know when the graph comes down and touches the x-axis at 2, it has to bounce off. It can't cross through. There's that multiplicity effect on the graph. Then it's got to turn around and come back at square root of 2, and then it crosses through because that has multiplicity 1. We know what the y-intercept is. I'm going to write down here. So it's not hard to get the y-intercept because we can plug into the original function, which was x to the fourth minus 4x cubed plus 2x squared plus 8x minus 8. So there's our original function. And if I plug in 0 for x, I get 0, negative 8. I get negative 8 for y. Now I'm not going to draw this to scale. I'm just going to say that's same scale. That's negative 8. So we know the graph has to come down to here. And then we know we got to go back up to that other 0 at square root of 2. So I think looking at the graph of this function is really informative. Now this graph is only approximate. It's not quite correct if you check Desmos for more accuracy. You're going to see the picture's a little bit different. We're not going to talk about it right now, but I don't really know where this graph turns around. There's no reason to think it turns around at negative 8. I think actually the graph dips down and turns around a little further over because we have no way of detecting that here. We'd have to plot a lot more points to figure that out. So this is very approximate, but the information about the zeros is very revealing. The y-intercept is easy for us to find. And I just wanted to point out the way we see that multiplicity of the 0 at 2 on this graph. So that's it for this problem. We're going to start talking about complex and imaginary numbers next.